Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if the way we measure things over time can be tricked by subtle changes? Well, this new study dives deep into that very question, looking at how to accurately track trends when the tools we use might be shifting slightly. Imagine you're tracking how well students are learning a subject over several years. You use tests, and to compare results from different years, you need those tests to be consistent. But what if some questions on the test get easier or harder for students just because of the year they took it, not because their actual ability changed? This is called item parameter drift, or IPD, and it can really mess with our understanding of trends. This paper looks at 5 different ways scientists try to get around this IPD problem to make sure their trend measurements are accurate. In many big tests, like ones to see how students are doing across a country or even internationally, clever tricks are used to compare scores from different years. They often use some of the same questions, called common items, to link the tests together on the same scale. But, as this paper points out, these common items aren't always perfectly stable. Sometimes item parameters lack invariance, meaning the difficulty or other characteristics of a question can change from one year to the next. This makes direct comparisons tricky. Differential item functioning, or DIF, is when people with the same ability have different odds of answering a question correctly, and IPD is just DIF in a time-traveling context. So, the big question is, how do we accurately estimate trends when these item parameters might be drifting over time? The researchers tested out 5 different methods to tackle this item parameter drift. First, there is concurrent calibration. This is like looking at all the test data from all the years at once and assuming everything stayed the same. Then there is fixed calibration, where you calibrate the first year S-test perfectly, and then you use those same question settings for the second year, kind of like locking them in place. Next, they looked at robust linking methods. These are smarter ways to link tests that try to identify and downplay the influence of those tricky drifting items. 2 of these they focus on are called Haberman linking and Hebera linking, and they use special mathematical tools like LP and L0 losses to achieve this robustness. It's kind of like using a special filter to ignore bad data points. The 4th approach involves detecting which items have item parameter drift first, and then re-estimating the trend using only the items that seem stable. They use 2 main tools for detecting this drift. A likelihood ratio test, which is like a statistical check for how likely a change is just luck, and the root mean square deviation, or RMSD, which is a measure of how much a question's performance deviates from what's expected. They looked at different cutoffs, or thresholds, for these statistics to decide when an item was considered to have drift. The 5th and final approach is regularized estimation. This method cleverly estimates all the parameters at once, but applies a kind of statistical shrinkage to the suspected drift effects, pulling most of them close to 0. This is done using something called the Smooth Bayesian Information Criterion, or SPIC. The idea is that most items probably don't have drift, so let's assume they don't, and only allow for significant drift if the data strongly suggest it. They tested this using different settings for the shrinkage amount. To see which method worked best, they ran a big computer simulation. They created a bunch of fake test data with different numbers of students, different numbers of questions, and various degrees of item parameter drift. They changed how big the drift was, how many questions were affected, and whether the drift was balanced, meaning some questions got easier, some harder, balancing out, or unbalanced, meaning all affected questions got harder, or all got easier. Then they ran all 5 approaches on this fake data to see how accurately they could recover the true trend. They were particularly interested in how well the methods handled unbalanced drift, which is often the hardest to deal with. So, what did they find after all this number crunching in the ideal scenario with no item parameter drift at all? All the methods basically worked fine, but when drift was introduced, things got interesting. Concurrent calibration and fixed calibration, the simpler approaches that assume everything is stable, performed poorly when there was unbalanced item parameter drift. Their estimates for the trend mean, and especially the standard deviation, got badly biased, and this bias didn't really get better even with more students. In the case of balanced drift, things were a bit better, but still not perfect. Concurrent calibration was generally unbiased for the mean but had issues with the standard deviation. Robust linking methods with certain settings started to perform quite well, especially Haberman linking. The real challenge came with unbalanced IPD here. The methods that assumed everything was stable really struggled. For the mean estimate, Haberman linking with a specific setting, P0, performed best overall among the robust methods. With very little bias, regularized estimation with SPIC also showed good bias control, especially with larger sample sizes. For the standard deviation estimate, Haberman linking across many settings performed well and was unbiased. But again, concurrent and fixed calibration and even some robust linking methods showed significant bias and poor performance. They did some deeper dives too. For the RMSD detection method, they found that the thresholds or cutoffs used to decide if an item has drift really mattered. Stricter cutoffs seem to work better, especially under unbalanced IPD, but sometimes these stricter cutoffs could lead to less efficiency, meaning they sacrifice some accuracy for robustness. Data-driven cutoffs, which adapt the threshold based on the actual data, showed promise, but still struggled with very large amounts of unbalanced drift. They also looked closely at the likelihood ratio test for detecting drift. They found that using a strict significance level, like the Bonferroni correction, helped control bias, especially under unbalanced IPD, but could reduce statistical power. Standard significance levels were okay for balanced drift, but became too lenient for unbalanced drift. Essentially, the LRT needed large sample sizes to work well and was quite sensitive to the chosen significance level. To see how these methods worked in the real world, they applied them to some actual synthetic reading data. This was like a test run using real-like data from students over time. They found that the different methods gave different estimates for the mean and standard deviation of student performance change, sometimes by a considerable amount. This highlights why choosing the right method is so important. For example, the difference between the lowest and highest mean trend estimates could lead to very different conclusions about how much students were actually learning. So, what is the big takeaway? When it comes to estimating trends over time, especially when there is a chance of item parameter drift, methods that don't assume perfect stability are key. Concurrent and fixed calibration were the worst offenders, failing badly under unbalanced drift. Robust linking methods, especially with careful selection of their settings, offered improvement. Haberman linking with specific robust settings and regularized estimation with SPEAK were the most consistent performers. The paper really emphasizes that the regularized estimation approach using SPEAK generally performed best across all their tested conditions, maintaining low bias and RMSEs. Now, no study is perfect. The researchers point out that they assumed the basic math model for the test questions. The 2PL model was correct. In reality, things might be more complicated. They also only looked at questions with right or wrong answers, not questions where you have to choose from several options. Future research could explore these methods with more complex test types and also look at what happens if the drift is not just in the question's difficulty, but also in how well it measures ability. They also suggest looking at longer time spans with more than 2 test points, which is common in real assessment. In conclusion, if you suspect item parameter drift, especially unbalanced drift, you should avoid methods that assume everything is stable. Haberman linking with certain robust settings or regularized estimation with SPEAK are much safer bets. For most situations, regularized estimation with SPEAK appears to be the top choice, offering a good balance of accuracy and stability. The paper really makes a strong case that understanding and addressing item parameter drift is crucial for accurately tracking progress and making reliable comparisons over time in educational and psychological assessments. It's all about making sure we're measuring what we think we're measuring year after year. Thanks for joining us on RUBIN'S Mind Lab. If you found this research interesting, give us a thumbs up, leave a comment below with your thoughts, and don't forget to subscribe for more breakdowns of fascinating psychological research. See you next time.